All right, so I guess we can get started then. So today it's going to seem kind of like a math class, which is going to be a little bit of a shock to the system, perhaps after the introduction that we did last lecture. So there's a podcast that I like called the DER Task Force that talks about all sorts of economic and business and policy issues in this area. And they pronounced the acronym DER DERS. And they had a vegetable that was called a podcast episode that was called Eat Your Veg Der Bowls. And so today we're going to be eating our vegetables. We're going to be doing some math, and it might look a little intimidating, but bear in mind that really what you need to take away from this lecture is a couple of simple formulas that you will code and you will use to simulate DERs, batteries, buildings, and so forth going forward. So don't be scared. Bear with me. So the outline today, we'll start by going over basically some notation and some reminders about linear algebra and calculus. So some of this stuff may be new to some of you. A lot of it will be review. And then we'll use some of the stuff that we talk about here in the rest of the lectures. So first we'll talk about solving linear ordinary differential equations, or ODEs, when the variable is a function of one variable. It's a scalar function. And then we'll apply that to a simple example of a battery. And then we will generalize what we did in basically one dimension for scalar ODEs to vector linear ODEs. And again, just we're doing this all for a reason. It's all building up to being able to actually model and simulate distributed energy resources. Okay, so starting from the very basics, I hope this is all familiar to everybody. A scalar is just a number, right? It's like a one-dimensional thing. And the set capital R here, I will use that to denote the set of all real scalars. So real means, kind of roughly speaking, something you can represent in decimal form, with any number of decimals, possibly an infinite number. And real here is by contrast to like integers, so -7 or 0 or 23, rational numbers, which is p over q, where p and q are both integers, or imaginary or complex numbers. And so when we say this notation here, alpha in R, or alpha is an element of R, that just means that alpha is a real scalar. So we'll use this notation of R and sometimes with superscripts on the R to basically denote dimensions of things, of vectors and matrices and so forth. Okay, so that's scalars. A vector then is basically just a list of scalars or a list of numbers. And the dimension of a vector, or the length of the vector, is just the number of numbers that it contains. And a column vector basically is a vertical list, and a row vector is a horizontal list. And so again, R with the superscript n, we use to denote the set of real n-dimensional column vectors specifically. So in a linear algebra class that you took in the math department, you may not have differentiated between column vectors and row vectors, but in this class we do. And that's because we really specify concrete bases, and we're talking about basically things that we can program and compute. Okay, so for some vector, call it A, an element of Rn, we write A either with these square brackets as this vertical stacked list of numbers, or with round brackets. So this is kind of like the notation you'd see for a point, x comma y, with parentheses. And the round parentheses here also denote a column vector, not a row vector. So a row vector we'd write with the square brackets rather than the parentheses, the round parentheses. And then AI, we just call that the I element of the vector A. So an element or a component or an entry, those all kind of mean the same thing. In other classes, you probably denote things, vectors, with some certain symbol, maybe a bold or an underline or an arrow on top, and we're not going to do that here. We'll make the dimensions of things clear, again, by using this kind of set membership notation. Okay, so that's vectors. A matrix then, rather than being a list of numbers, is an array of numbers, and a rectangular array specifically. And the size of a matrix, we say, is just the number of rows by the number of columns. And we say R m times n, or m by n, is the set of real matrices that have dimension m by n. And so we write some A basically in terms of its components, and I'll use capitals. Some people will use a lowercase a in here, but I'll use the capital A, and then just components 1, 1, all the way down through M1. So that's the first column of A, all M rows of it. And then, all the way over to 1n. So that's the nth column of A. And then we again say that aij, that's the ij element, row I, column j of A. And then the transpose of a matrix A, basically you just take all the rows and write them as columns. So here, rather than having A11 through A1n as a row in A, we have it as a column in A transpose. And of course, if you take the transpose of the transpose, you get back the original matrix. Okay, so matrices can be viewed as a generalization of vectors, which in turn are a generalization of scalars, right? So we can view a matrix that is an Rn by 1, basically a 1-column matrix. We view that as a vector. And similarly, a 1 by n matrix, we view that as a row vector. And then, of course, a one-dimensional vector A, that's just a scalar. And so when we write basically Rn by 1, we'll forget about the by 1 thing and just write Rn, again, to denote column vectors. And instead of R1, we'll just write R to denote scalars. And by the way, folks, if you have questions, either in the room or on Zoom, please just speak up and stop me. Yes?
You would probably not use RM. Like, should we ever assume that if you're using N versus M, but there's only one of them, that's always going to be a column?
So the question is, what if we write Rm? Basically, should we assume that that's a row vector or something like that? No. So the symbols that we use for the exponents or the superscripts don't really matter. So we could use P or Q or M or L or something like that. And it's always going to denote a column vector. Good question. Thank you. Okay, so scalar multiplication, very easy. I think everybody probably recalls this. So if you take a scalar alpha and a vector A, we do alpha times A. Well, that's just alpha times each of the entries in A. And it's very easy to show that that's the same as A times alpha. So, so the order of multiplication between a vector and a scalar doesn't matter. Another way of saying that is that a scalar and a vector in multiplication commute. So that means order doesn't matter, basically. And then for a matrix and a scalar, again, it's the same thing. We commute. And the definition is the same as for vectors. We just take the scalar alpha and multiply it by each of the components of the entries in the matrix A. Okay, so that was basically multiplying a scalar by stuff. How do we multiply two vectors together? Well, there are a number of ways. And the main one that we'll use in this class is called the inner product or the dot product. So if we have two vectors of the same dimension, call it n, the dot product is defined as the product A transpose times B. And so that's just the row vector, A transpose, times the column vector, B. And we get that basically by multiplying the first element by the first element and so forth, and then adding up all those products. And in other books, this may be, or other classes, you might see this denoted as A dot B, or in a physics class, you might see it as this thing with like bra and ket, the sort of bracket notation. That's also called a scalar product or a dot product, but it all means the same thing. And then one example that we'll use a fair amount is if you take the dot product of a vector of all ones. So here, this is an n-dimensional vector with n in every element, or sorry, with 1 in every element. If you take that and you multiply it by a vector, you just get the sum of the elements in the vector. Okay, so that's vectors times vectors. So let's talk about multiplying matrices by vectors. So if we have some matrix A, in general, n by n, and a vector B, say an n-dimensional vector, when you multiply A times B, you just basically take the 1, 1 element of A, multiply it by B1, and so forth, 1n times Bn, and we form it in this way. And there are a couple of interpretations of matrix times vector multiplication. So one way to look at this is by taking every row of A. So the first row here is A11 through A1n, and taking the inner product between that row and the column vector B. So that basically forms the first entry in the matrix AB. And then you do the same thing for every row of A. So we get down to the M row of A, take its dot product with B, and we get the bottom entry in AB. And this thing here, what are the dimensions of the product AB if we have A m by n and B in Rn? Yeah, m by 1, right? So it's a vector of like that. Sorry, m. Another way to look at matrix times vector multiplication is as a linear combination of the columns of A. So if we look at the first sort of set of terms up here in the definition of AB, we can see that that's basically B1, a scalar, multiplied by the column vector A11 through AM1. So that's this column vector here. And then we have a bunch of those terms all the way over to Bn, multiplying by the nth column of A. So this is in linear algebra class, you talk about like bases and spans and linear combinations and all that sort of stuff. And this is basically why you talk about those things, is because matrix multiplication times a vector can be interpreted basically as a linear combination of the columns of A. And so this leads you to conclusions about invertibility and stuff like that. Okay. So one example that we'll use a lot involves the identity matrix, which we just denote I. And sometimes you can put subscripts on this, like for example, n times n as a subscript, just to denote the dimensions of or the size of that matrix. But usually the size of it should be clear from context. So, if B is n by n, then the identity is a square matrix. Sorry, if B is an n vector, n-dimensional vector, then the identity is always square, and to multiply B, it has to have dimension n by n. So if we take the identity times the vector, you just get back the vector. Okay, and then last kind of review of these matrix operations is what happens when we multiply a matrix by another matrix. And here is where, in my experience, people sometimes get a little bit confused with the order of operations and commuting and things like that. So it's good to be careful. So for A in R m by n, so an m by n matrix A and an n by p matrix B, the ij element, so the one that goes in row I and column j of the product AB, is defined as the inner product, essentially the ith row of A times the jth column of B. And this syntax, again, only parses. Like if you try to program this in Python or MATLAB or something like that, you'll get an error unless the A and the B matrix have the appropriate dimensions. And that means that the number of columns in A, so the second dimension of A, has to equal the number of rows of B, the first dimension of B. So we want to be careful, and we'll do a little bit of playing with matrix multiplication and stuff like that in the next couple of lectures and homework. So you want to be very careful in general. Sometimes it's really tempting to say, oh, I have a product AB, and if I could just twist the order around and call it BA, it would make life a lot easier, right? I'd get a quick solution or something like that. But in general, this is not true. So first of all, AB equal BA, that syntax only parses if A and B have very special dimensions, and they have to actually both be square, and they have to be the same size. So they both have to be n by n for some value of n. And then even if it parses AB equals BA, so they're both square of the same size, then we only get this equality AB equal to BA in some very special cases. So usually, so that's called A and B commuting. And there are some theorems and things like that about when that happens for matrices, and it's usually not the case. So be careful with that. And then I won't talk too much about solving systems of linear equations, but when we do that, we typically invert matrices or do something computationally equivalent to inverting matrices. And so if you have an invertible matrix, so to have an inverse, a matrix must be square. So if it's square and non-singular, meaning that determinant is not zero, then you get this existence of this inverse A to the power -1. And it's defined such that if you multiply on the left by A, or if you multiply it on the right by A, either way, you get the identity. So this is meant to look like if you had a scalar alpha, alpha times 1 over alpha is equal to 1. So that equation works as long as alpha is not equal to 0. Okay, and then in the second half of this lecture, we'll talk a little bit, when we're talking about solving systems of differential equations, we will talk about basically matrix-valued functions. So this may be something that you didn't see before in a linear algebra class or a calc class. So if we have this notation, A, that takes arguments in R and maps them to stuff in R m by n, that means that A is a function that takes scalars as inputs, right? So that's what the R thing here is. It's denoting just numbers. And it outputs matrices, m by n matrices. So if we call the independent variable t, some real number t, we write the thing A of t as just the components, A11 and so forth, evaluated at basically time t. So A of t at any given value of t, this is a matrix. It's a concrete thing. You could ask Python to output, and it would give you, all the numbers and all the entries in the matrix. And then aij, this thing in here, this is a function, and it's the kind of function that we deal with in basically first-year calculus. So this is a scalar valued function that takes scalars as inputs. Okay, so we want to talk about how to take derivatives of these things, and it's quite easy. It's very natural. It's what you would think, basically. So the derivative of this matrix valued function of a scalar is just the derivative of each of the components of the matrix. And then we get a product rule for this type of function that looks a lot like the product rule for scalars, right? So the derivative of the product A, B, where A is a vector, sorry, a matrix valued function, and B is a vector valued function. So that product, just like in freshman calculus, you learn that the derivative of the product FG is F prime G plus FG prime, right? So this is that kind of formula. We have A times the derivative of B plus the derivative of A times B. So this will come up in later in this lecture. And then same thing with integration. If we want to integrate one of these matrix valued functions of a scalar argument, we get basically just the integral of each of the components in the matrix. And then we have a convenient formula that'll show up again later in this lecture that has to do with simplifying these integrals. So if you integrate the derivative of a function, you get back basically the delta of the function. So capital letters rather than lowercase letters. Not a lot of new stuff going on here, but I just figured let's get it down to kind of set levels before we dig into the actual content today. And the last bit here is it's convenient to write matrices as what are called block matrices. So here we have a matrix A that's made up of smaller matrices. You could call them blocks or submatrices. And so sometimes it's convenient to write stuff in this way. You have to be pretty careful about dimensions when you do it. So B and C have to have the same number of rows, right? So that basically this dimension here is consistent. And then similarly, D and E have to have the same number of rows so that this dimension here is consistent. And then the number of columns in B and D has to be the same, and the number of columns in C and E has to be the same. So sometimes when you're programming stuff, you can use this kind of block matrix representation to build bigger, more complex matrices out of smaller, simpler ones. And you can do this notation at least in MATLAB and in Python. Okay, so with that kind of background out of the way, let's talk about solving first order linear, scalar, ordinary differential equations. So I think, again, this will be review for everybody. This is probably the first thing that most people did in their kind of undergraduate differential equations class. But there are a number of ways to approach this, and we're going to approach it in a particular way, which might seem convoluted at first, but there's a reason that we're doing it in this way, which is that's the way that you basically the analogous process allows you to get general solutions for systems, linear systems of differential equations. So we'll do the process first in the scalar case, which is a little easier to understand, and then we'll do it again in the vector. So an ODE, an ordinary differential equation, has the variable is a function, right? It's a scalar valued function of scalars. So it's a function from R to R is another way to say that. And it relates that function to its derivatives. And because we're dealing with a function of one variable, not a function of multiple variables, the derivatives are ordinary, not partial. Right? So that's where ordinary in the term ordinary differential equation comes from. So we can talk about some examples here. So here we have the first derivative of x is e to the minus t times the function value itself minus some constant. We could have sines and cosines. We could have higher order derivatives. So here we have d squared x by dt squared, and here we have a third derivative of x. And over here on the right-hand side, we have sine of x. So this is a nonlinear term. So any of these, in general, if you can solve it, that means basically finding an expression for x as a function from R to R. And it turns out, and this is something that most people, I think, don't get in their undergraduate class, but most ODEs you can't solve analytically. So like no matter how smart you are and how hard you try, you cannot write down a function that solves the ODE. But almost essentially every ODE can be solved analytically, or sorry, numerically. So there are basically computational methods where if you provide input data, right, like what is this function or whatever, e to the minus t, you provide input data and you run an algorithm and it can give you back to very good precision the numerical value of the function at any time. Okay, so then we categorize ODEs. So the order of an ODE, there are various categorizations, and I won't go through them all, but just the ones that are relevant today. The order of an ODE is the highest derivative that shows up in the equation. And then an ODE is linear if you can write it in this particular form, where on the left-hand side you have the highest derivative, the nth derivative. And then on the right-hand side, you have a bunch of functions of the independent variable t, which in this class usually will represent time. So you have a bunch of functions of time times lower order derivatives of the function itself, x. And then we have one leftover function here, b. This is the non-homogeneous term or whatever. Okay, so we can categorize the three examples that I wrote down. This one is linear. So even though we have a weird function of t in here, it's not, at plus b, a linear function of t. It's an exponential, a nonlinear function of t. That doesn't matter. The ODE is still linear because this thing is basically written as a linear combination of x and its derivatives. This one here is second order because we have a second derivative showing up. And the right-hand side is not a linear function of x, right? It's sine of x, a wiggly nonlinear thing. So this is a nonlinear ODE. And this is the sort of equation that would show up like in a pendulum problem in mechanics. And this one, because it has a third derivative, well, it's third order, and it is linear because it just has these kind of linear combination weighted by functions of t of the function and the derivatives of it. Okay, so why do we do that categorization? Basically because it gets us to a class of problems that we can solve analytically. So we're going to only talk about first order linear differential equations to begin with, and then we'll talk about higher order ones, which actually get recast as sort of vector or systems of differential equations. And we'll talk about how to solve those a little later. So there are various kind of boundary value problems. You can have final value problems with ODEs, but what we'll do in this class is always an initial value problem. So I give you basically the starting point of the function x initial, and then I give you the function that describes its evolution. And because we're only thinking about first order linear differential equations, they always can be written in this form here, where you have the first derivative on the left-hand side, and then you have basically an ax plus b on the right-hand side. Okay, so in an undergraduate ODE class, you may have learned about first solving for the homogeneous solution and then finding the non-homogeneous solution and then having a sum of them be the general solution and stuff like that. And that works. But again, we're going to solve it in a slightly different way. And I'm going to go through some steps here. There's going to be like 2 or 3 slides of a derivation. And I'm sorry if it looks kind of spooky. You don't need to memorize the whole derivation. You just want the formula that comes out at the end. But I think it's worth going through the steps so that you guys know kind of where these things come from. Okay, so to begin the solution process, we take the ODE, so not the initial condition, forget about that for now. Just take the equation on the right here and multiply it by some function g. And we want g to be positive to avoid the case where g is 0, and you take a meaningful equation, you multiply by 0 on both sides, and you get basically a meaningless or a trivial equation. Okay, so multiply by a positive g, we get dx dt by g, and then we move over this term, the ax, move it to the left-hand side so it becomes negative, and we multiply by g as well. And then the right-hand side, it gets multiplied by g. Okay, so this, I think, is just a rewriting of the first equation here. And then it turns out that that is equivalent to the bottom equation here. D by dt of the product xg is equal to gb. And where that comes from is the product rule. So again, if we have the derivative of product xg, well, that's just x prime g plus xg prime. And so if our function g has this particular special form where its first derivative is negative a times the function itself, then we get this nice form down here. So you can see basically where this comes from. On the left-hand side, we have x prime g. That shows up in the product rule as well. And then we have xag. Down here, we have xg. And so if this equation is satisfied, then basically we get the equivalence of these two equations. All right. So this equation here, we're going to come back to in 2 slides. But first, we're going to think about what function g can we get that satisfies this equation. Okay, because if we can get that, then we're basically there. We basically are at our solution. So no surprise, this thing turns out to be the exponential. And this is essentially why Euler defined the exponential function back in like 1780 or whatever, was to solve equations like this. So let's just make a guess. Let's guess that it's the exponential of the negative integral of this function a, the coefficient function here, dt. So first of all, what does this mean? It's a little bit of sloppy notation, but this is a sort of an improper integral here. So this thing is basically any antiderivative of the function a. So there can be an infinite number of those, right? Anything plus some constant c of integration works. But we can use 0 basically for that constant of integration because it's simple. So for example, if we had cosine of t up here in the original differential equation, if that was multiplying our x, we could just use the integral of cosine, which is sine, right? Derivative of sine is cosine. Okay, and we chose this thing. So this thing is always going to be positive, e to the negative integral of a dt for any a, because this thing up here is just a number, and e to any number, z, is always positive. So even if z is negative a million, e to the z is always greater than 0. Okay, so that's our guess. Now we need to check basically that this equation that we hypothesized is satisfied. So to do that, we just take a derivative of this thing. So we just write down the definition, the right-hand side, take its first derivative. Well, the derivative of e to anything is, again, e to that same stuff times the derivative of the inside stuff, right? This is the chain rule for scalar functions. So we just write down the function again, and then we multiply by the derivative of the inside thing. But this thing here is an antiderivative of a, so its derivative is just a. Okay, so then we get that the whole time derivative of g is just equal to negative ag, and that's what we were looking for. So it's sort of easy after the fact to kind of guess and check. It's much harder, I imagine, for someone in the 1700s to have come up with this kind of out of nowhere. But that's why there was a genius. So, okay, all right. So now we've figured out what this function g is. So let's go back to the equation that we ended with on the slide 16 here. And we'll go back to that and proceed from there to actually write down the solution of the differential equation. So this is that same equation. That's our starting point. On the left-hand side, we have the derivative of xg. On the right-hand side, we have gb. And we know what the value of g is. Okay, so now let's take the integral on both sides, and we'll do a definite integral from some initial time up to the time t that we're interested in at kind of evaluating the solution of the ODE. And on the inside, then we're going to change the variables from t to tau, just to basically avoid confusion with the limit of integration being t over here. Okay, so we're just integrating the left-hand side, integrating the right-hand side, and introducing this dummy variable of integration, the tau. Okay, now we apply the fundamental theorem of calculus because we're integrating the derivative of the thing. So that just ends up being the delta of the thing, right? And the thing on the inside here is the product xg. So we get xg evaluated at the upper limit of integration, which is t, minus xg evaluated at the initial, t initial. And then the right-hand side hasn't changed at all. So now you can kind of see that we know what g is, we know what b is. This is given to us in the problem statement. We know t initial, so we can evaluate g at t initial. We are given x at t initial. That's the initial value we're given in the IVP. And we know g over here. So now we just basically do a little bit of algebra to solve this thing for x, and then we're done. So that's our last step here. We add this over to the right-hand side, divide through by g, and we get an explicit function, an analytical function for x, the solution. So to summarize, right, we have an IVP of this form, a linear first order IVP. The solution can always be written in this form here, where g is e to the minus integral of a dt. Okay, so I promise this will be useful, and the reason for it is that a lot of DERs basically can be written in this form. Batteries, for example, I'll talk in just a second about how a battery falls into this general form. But I want, basically, there's a bunch of weird stuff that shows up in this derivation, in particular, this function g, and knowing what the antiderivative here of a should be. So I'm going to give you a concrete example. It should be quite simple. This is not a hard problem. You can just take it and plug it into, Mathematica or Wolfram Alpha or whatever, and it'll just spit out the answer. It's not difficult at all. I just want you to go through and basically parse the formula so that you understand kind of what each of the terms that show up in the formula are. So it should only take, hopefully 5-10 minutes. Okay, and then we get basically some special cases under simplifying assumptions. So if that function a of t that was multiplying x in the original differential equation, if that is constant, then we get a simpler looking formula. So the antiderivative, that function g, basically disappears because it's just e to the ta. So this is a nice simple formula. And then if b is also constant, then we can easily evaluate this integral. So rather than b being, e to the t sine of t or something like that, it's just a number. So we can pop it outside the integral. And then we evaluate this thing. And I won't go through all those steps, but you can turn the crank. It's just integrating an exponential. And you get this function here. And when we get to solving systems of higher dimensional, not scalar systems of ODEs, the solution will look a lot like this. But rather than having the scalar exponential in here, it'll have an object called the matrix exponential. And we'll talk about what that is and what it means. Who's heard of the matrix exponential before? What class did you do matrix exponential in? Numerical methods, yeah, that makes sense. Yeah. It comes up a lot in kind of graduate controls classes and linear systems classes and signal processing and stuff like that as well. Okay, and then a very special case, if a is equal to 0 and b is a constant, well, then our initial value problem is just essentially like a constant velocity motion problem. So the IVP comes from basically dx dt is equal to b. So if you think of x as the position of some object, dx dt, well, that's just the velocity. And so here we're saying it's constant velocity. And we know from physics that the solution to that thing is just the initial position plus t times the velocity, basically. So this is not useful for us. It's just kind of verifying that the formulas we've written down make sense. Right? So if you take a equal to 0, they simplify to this form here, which is what we expect. Okay, so that was a lot of basically math background and then scalar ODEs. So let's talk a little bit about how that stuff applies to the world of energy. So we'll begin with an example of a battery. So a battery is also known as electrochemical energy storage. So basically you use electricity to run chemical reactions, and that stores chemical potential energy. And then to get that energy back out, you essentially let the reaction run in the opposite direction, and it generates a voltage which can be used to generate electricity or current. So a battery model, a simple one, is just dx by dt on the left-hand side is negative x over tau, plus the chemical charging or discharging power. So here P chem is to distinguish from P electrical. We'll talk about more of how all this stuff works kind of physically in a lecture on batteries in maybe a week or so. But just think of this as the charging power, essentially the amount of the rate at which you're putting energy into the battery. So if this thing is negative, then you're pulling energy out of the battery, discharging. And X is the chemical potential energy that's stored from these chemical reactions. And tau is called the time constant, which has to do with self-dissipation. So what this basically means is if you have a higher charge in the battery, there's some chemical potential somewhere, and that leads to sort of self-discharging or dissipation, unplanned discharging of the battery. And that's faster for when you have more charge stored in the battery, basically. Okay, so this thing is a first order linear, right? It has an A, which is negative 1 over tau, and it has a B, which is this P chemical. So it's linear. It's first order. We only have the first derivative showing up of the function X here. So it's a first order linear IVP, and it has a constant function A of t. It's just A, negative 1 over tau. And so let's apply the formula that we had for when the function B of t, for when that is equal to a constant. And let's assume some initial condition that at the initial time, we're at some initial value x initial. So this could be 20 kilowatt hours or something like that. So if we go back and we look at our formula here, we're in the A constant and A not equal to 0, right? Because tau is positive. And B is constant. So we're in the world of using this second highlighted formula here. So I won't go through all the steps, but you can basically take this formula and plug in the definitions of A and B, and you get the general solution, assuming constant charging power. And it takes this form. So we have a exponential decay thing here, multiplying the initial conditions. And then we have an exponential growth kind of thing here, 1 minus exponential decay, multiplying by tau times the charging power. Is everybody on board with this so far? Any questions about this? All right. So what is the limiting behavior of this thing? So as basically t goes to infinity, we've been charging the battery at this constant rate for a super long time. The charge state approaches some final value, which turns out to be a steady state. And steady state just means that the derivative, the time derivative that shows up in the differential equation is equal to 0. So if we reach that steady state, x is equal to this final value, then we can look back at the ODE and we can plug in the values here. So we have on the left-hand side the derivative, and on the right-hand side we have negative x over tau, and x is equal to tau p. Tau's cancel, we have a negative p here and a plus p here, so we get 0. So this tells us that if we land in that final state, then we don't change at all, we just stay there forever. Okay, so in that case, with constant charging power in this first order linear ODE, the solution ends up being a mixture of the initial state and that final state, tau p. So a mixture, just like in chemistry or something like that, a mixture can always be written as some number lambda times the first thing that you're mixing in, call it Z1, plus 1 minus lambda times the second thing, Z2. So lambda here basically is interpreted as the percentage of the mixture that is Z1. So if you have something 90% Z1 and 10% Z2, we have lambda is 0.9 and 1 minus lambda is 0.1. Okay, so our thing tau is positive, and t we assume is greater than t initial. So this whole thing, e to the minus t initial divided by tau, that's going to be between 0 and 1 because it's e to a negative number, basically. So e to the minus infinity is 0, e to the 0 is 1. And for a negative number anywhere in between, we're somewhere between 0 and 1. So we can interpret this thing, the e to the minus t on tau, we can interpret that basically as a weight in a mixture formula. So again, assuming that the charging power is constant, we get that x is a mixture of the initial value, right, weighted by this thing, plus the final value weighted by 1 minus that same. Okay, so if we define the gap, basically the distance that we still have to go to reach that final state, if we define a variable y, which is the normalized version of that gap, final minus x divided by x final minus x initial. Then it turns out, you can do a little bit of algebra, but it turns out that y of t is equal to just e to the minus t minus the initial time divided by tau. And that just comes from taking the expression for x, which we derived a slide or two ago, and plugging it in up here and doing some algebra. So after n time constants, basically t equal to n tau plus the initial time, we get that basically 100 e to the minus n percent of that initial gap remains. So when we're at time t initial, 100% of the gap remains. Basically, we're at the initial condition. We haven't moved it all toward the final condition. After one time constant, 37% of the gap remains. So we've eaten away 63% of the distance. Two time constants, we've eaten 86%. After three time constants, we're almost there, right? 95% of the way there. And then after 4, we're 98% of the way. So here's what that looks like. This is a classic, basically exponential approach or exponential decay kind of a curve. So we start on the x-axis, we have time, and on the y-axis, we have x, so the energy stored in our battery. We start at some initial value, and here I'm saying x final is greater than x initial, so I'm assuming we're charging here rather than discharging. But this is like you plug in an electric vehicle, and it charges at constant power, basically until it's full. And so we see this exponential approach here. One time constant, we're at the, whatever it is, 63 or 65%. Two time constants, we're at 85% roughly, and 3, we're about 95%. So when we simulate stuff, we'll often see behavior like this from the state variables that we're working with, whether it's temperatures in a building, you know, temperature in a water heater, you know, energy stored in a battery or stuff like that. Okay. So the math gets a little hairier in this section, and we start using more of the linear algebra that I talked about in the first section. So are we feeling prepared for that? Any questions about anything we've covered? Cool. All right, so a vector ODE basically is a generalization of a scalar ODE in the same way that a vector is a generalization of a scalar or a number. So just to recap, a first order linear scalar ODE has this form, right? Derivative, first derivative on the left-hand side, and then an ax plus b on the right-hand side. And the input data basically are the functions a and b, and then typically an initial condition x. And the variable we're looking for is this function. Okay, so then a vector ODE basically just generalizes that same form. So again, on the left-hand side, we have a first derivative. And on the right-hand side, we have an ax plus b kind of a thing. But now a, rather than being a scalar valued function, is a matrix valued function. So in general, a is an n by n matrix if x is a function in Rn. So that would be an nth order linear system of differential equations. And then, so if x has dimension n, then ax has dimension n, and that means that this thing b here also must have dimension n. So this is a function basically from R to R. And now the variable, rather than being one function that maps, you know, say time into position or time into energy, it's a list of n functions that map time into, say, a bunch of different positions or energies or temperatures or other kind of state variables. So solving this linear vector differential equation amounts to basically finding an expression for x. And we can write this same equation here, kind of our canonical linear vector ODE. We can write that in components, and maybe it's a little bit more clear. So basically, our variable x we can write as a list of n functions, x1 through xn. So the left-hand side thing here, this dx by dt, is just a vector of all the time derivatives of all the x functions, xi functions. And then the matrix here, again, a of t, so that's just a bunch of functions a11 through ann. And actually, I'm mixing up notation a little bit here. I said I would use capital A to represent the components of a matrix, and now I'm using the lowercase a. So anyway, I'll make little mistakes like that as I go here. But anyway, it's basically A is just a bunch of functions, n squared of them. And then x, we have all these functions as well. And on the right-hand side, b, we have the functions, again, just b1 through b. Okay, so let's think about how to solve this thing. But before we do that, I just want to make the point that if you have an nth order linear, a differential equation where you have a scalar function as the variable, right? Some x from R to R. You can write that nth order linear equation as a system of n first order linear differential equations. So this is a common move that you do in a dynamics class, for example, where you might have two states, a position and a velocity. And then you have a differential equation which relates acceleration to the position and velocity. So a common move then is to define a state space basically that's x and x dot, and then kind of go from there. So here I'm just basically showing how to do that process in general. So here I've introduced a little bit of shorthand just to kind of keep the math that's on the slides a little bit cleaner and shorter. So x to the parentheses n, that means the nth derivative of x. So dnx by dt to the n. And then I've dropped the time arguments as well, but you can imagine that these things, the I functions, that those are functions of time, and B is also a function. Okay, so the basic move here is to define a vector variable, call it z, which is just a list of x and all its derivatives. So this would be x, and then the next entry would be, x dot or dx dt, and then we go all the way down to the n-1 derivative. And we stop before the order that shows up in the differential equation. Okay, and then we want to write down basically a differential equation, a vector differential equation for z. So on the left-hand side, we write down basically dz by dt. So what that does is it takes, the order of the derivative that shows up in each of the entries of z and basically increases it by 1, right? Because, for example, x to the n minus 1, that's the n minus 1 derivative. You take another derivative of that, you get the nth derivative. So this thing here is dz by dt. And then we have a bunch of equations, basically. So the first one says that the first derivative of x, well, that's equal to, and then over here, the second entry that would show up in this list is x dot or x1. So this row just says have 0 everywhere and then pick out only the first derivative of x when you do this matrix multiplication. And then that derivative, you're just saying, look, x dot equals x dot, basically. So the b function doesn't show up anywhere in. And then you just go down the line, basically doing that same process. So, the second derivative equals the second derivative and so forth until you get all the way down to the n minus 1 derivative. And then the differential equation basically shows up only in the bottom row here. So now we just write down this equation. Xn is equal to a naught times the function x. So that's the term that shows up right here. And so on until we have an minus 2 times this term here, and then an minus 1 times x, n minus 1 derivative. And then we have the forcing term here, b, shows up only in that bottom equation as well. So this is one way to do this. There are also other ways that you can take an nth order linear differential equation and turn it into a system of n differential equations. So you don't have to use this particular form. You could define a weird variable that had, x and then 4x plus x dot or something like that as the second entry. And you could still do this basic process to get a system of equations. So if we then write this thing basically in matrix vector form rather than element-wise, we get on the left-hand side dz by dt equals a of t. This big matrix here is our a. This thing here is just our z. And then we have a new kind of forcing term c, which is basically just 0 everywhere, and then the function b at the bottom. So this has that form that we started with when we introduced the kind of canonical form for a vector linear differential equation. So it's z dot equals az plus c. So who has seen something like this before, like maybe in a dynamics class? Okay, good. Okay, all right, so that's showing basically that you can take high order linear scalar differential equations and write them as vector differential equations. So now let's talk about how to solve these things. And it turns out that the solution process looks just like the process that we went through kind of in meticulous detail for the scalar case. So we start with our IVP. We're given some initial condition here, which is an Rn. And then we have our ODE. And it turns out that when A is time varying, so unlike the scalar case and the vector case, there just is no analytical solution in general. There are some special cases where you can find one, but you can't write down a general solution in the same way that we did in the scalar case. So we'll assume from now on, basically, that A is constant. So rather than being a function of time that has a matrix value, we'll just say it's a matrix. So if A is just a matrix, an n by n matrix, then this thing, it turns out, has a solution that looks almost identical to the one that we wrote down in the scalar case. So it's E, this is a scalar thing here, t minus t initial, that's just some number. But now we have E to a number times a matrix. So this is the matrix exponential that I mentioned earlier. So we have matrix exponential times the initial condition, and then we have plus the matrix exponential now times the integral of a vector in here. So this is a matrix, an n by n matrix times an n by 1 vector. So this whole thing is a vector. So now this thing here is an integral of basically all the entries in an n-dimensional vector. And then we take that vector and we multiply it on the left by another square matrix, the matrix exponential here. Okay, so we'll talk about what this is and a little bit about how to compute it. As Alex mentioned in a kind of computational methods or computational linear algebra class, you probably would talk a lot about fast and stable numerical methods for computing this thing, EDM, and MATLAB. So a lot of people think MATLAB, the mat stands for like mathematics, but actually it stands for matrices. MATLAB was basically built to do matrix and vector type calculations. So there are very fast and robust methods in MATLAB to compute this thing, the matrix exponential. By the way, if I'm going through slides too quickly for people who are taking notes by hand, just let me know and I will slow down happily. But also know that all these slides are up online. So if you can't keep up, you can always go back and look through them later. Okay. So what the heck is this thing? What does it mean to take E to a matrix? So is it just taking E to every value in the matrix? It turns out that the answer is no. It's more complicated than that. Instead, we define this thing in the same way, basically, that you define the scalar exponential, essentially through a power series definition. So that definition requires some notation. So if we have a square matrix M, we define M squared as just M times M. M cubed is just MMM, and so on. And this notation only works for square matrices, right? So if you have an M by N matrix where M and N are not equal, then M times M, that doesn't parse because you have M by N times M by N. And again, the column dimension of the first matrix has to equal the row dimension of the second matrix, and so it just breaks. Like you get an error from your code, essentially. Okay, so you may remember from like Taylor series chapter in your calculus class a million years ago that we define the power series definition of the exponential. It looks a lot like this for a scalar function. And so we just basically extend that to be matrix valued. So here we have the identity matrix rather than a one. Then we have the thing itself. And then we basically have this kind of power series expansion here. So 1 over 2 factorial times the thing squared, 1 over 3 factorial times the cube, and so on. And this is an infinite series. It goes on forever. So you can imagine already one kind of simple way to compute this, which turns out not to be the best or even numerically very good, but you could just apply this definition and then truncate it after n terms. You could truncate it after a million or a billion or whatever terms. And the more that you kept, in theory, the more accurate your approximation would be. But it turns out that due to rounding errors and other kind of numerical effects, it ends up not being that accurate or that fast. And so there are better ways to do it. So why do we define this thing? Well, it turns out that it shows up kind of in the same way that the exponential showed up in our derivation of the solution for first order linear scalar differential equations. The matrix exponential shows up in the solution for the vector valued ones. And we basically define it because of this relationship that if we take its derivative, e to the tm, with respect to t, we get back basically m times e to the tm. So it looks just like it does in the scalar case, right? The derivative of e to the at is just a e to the at. And you can show this rather quickly. So you basically just write down the series in here and then just roll through term by term, taking the derivatives. So derivative of the identity matrix, that has no dependence on time, so it's just 0. That's a 0 matrix, so it drops out. And then here, derivative of t times m, well, that's just m. Again, the t basically drops out and so forth. And you roll through in that way, and you get back this. Factor out an m on the left. And actually, in this step, you could also factor out an m on the right equivalently, right? Either way works. So I've written it one way here with the m here, and then that leads to an m down in the conclusion. But you could also factor out an m to the right, and you'd have an m here on the right instead. And then we would get e to the tm and that thing times the matrix m on the right. So it turns out that those are the same. Either way works. So does the derivation make sense? Yeah, okay, cool. Okay, so that's the basic definition and the reason that we define it in such a way. Now let's basically just write down a few implications of that. So here I'm just copying over the thing that we showed on the previous slide. That the time derivative of this thing, e to the tm, you can write either as m, e to the tm, or e to the tm, m. So a way to say this would be that m commutes with e to the tm. The order of matrix multiplication doesn't matter for this thing. E to the 0 is equal to the identity, it turns out. And that's pretty straightforward to see from the definition. And here, again, this is like, this equation is hiding a lot of potential ambiguity. So here 0 is not a scalar. 0 is a n by n matrix, where every entry in that matrix is a 0. And then I is an identity matrix, so it's 0 everywhere except for the main diagonal, and on the diagonal it has 1s. And then if you have two scalars, t1 and t2, if you do e to the t1 plus t2m, you get e to the t1m times e to the t2m. So this again looks just like the rule for the scalar exponential. You need to be careful because not all the rules for the scalar case work in the matrix case, but these are the ones basically that do and that are useful for us. And then it turns out that e to the m is always invertible. So even if m is not invertible, e to the m always is. And its inverse is always just equal to e to the negative tm. And so this, again, this looks just like the scalar formula. And you can show this pretty quickly. So you take e to the tm multiplied by e to the negative tm. Well, from this rule, the third one, we get that that's equal to e to the t minus tm. But t to the t minus t, that's just 0. So then we get e to the 0m. But 0 times any matrix is 0. And so we get e to the 0. And then that's the identity. So this basically shows that this thing is the inverse of this thing, because when you multiply something by its inverse, you get 1 by definition. And then one last property has to do with integrating the matrix exponential. So in the same way that we have a rule for derivatives of the matrix exponential, we can get a rule for the integral. So if we integrate from, say, some value t1 up to t2, e to the tm dt, we get m inverse times essentially the difference, the delta in e to the tm. And just like for the derivative rule, the m could show up on the left or the right. Here for the integral rule, the m inverse can show up either on the left. Okay, so why is this true? So we start with our formula. Our d by dt e to the tm is m e to the tm. So that's just the first rule. Basically, that was the whole reason that we defined this object in the first place. So we start with that. And then we'll just integrate both sides. Right? The thing we're trying to get a formula for has an integral in it. So let's do that. Integrate both sides from t1 to t2. And when we integrate the right-hand side, well, m has no time dependence in it. So so that thing pops outside the integral, basically. And then we just have the integral of e to the tm on the right-hand side. And then here, this is the fundamental theorem of calculus. So that's why I wrote it down on the page when we talked about matrix valued functions of one variable, essentially. So we know how to evaluate this derivative here. So again, if we integrate the derivative of a thing, we get back basically the delta in the thing. And here, the stuff that we're looking at is e to the tm. So we get e to the t2m minus e to the t1. And we haven't done anything on the right-hand side here. Now, if we multiply both sides of this equation by m inverse, then the m's cancel. The m inverse on m cancels on the right-hand side. And on the left-hand side, we have this here. Yeah, Rush.
Can we change the order of multiplication in the first line? I assume most of those are
in the very first line here? This one?
The integration, the first line. If n
Oh, up here. Yes. So you can have the m inverse either on the left-hand side or over here on the right-hand side. Is that what you're asking about? Yeah. And so to prove it, so I proved it for the first term here, the one that shows up with the m inverse on the left. And to do the proof for the one that has the m inverse on the right, you just start with the second version of this formula. So rather than m e to the tm, you have e to the tm m. So if you start with that, and then you run through the same steps in the proof, you can imagine you have an m here and m here. And so then you right multiply by m inverse, and you kill the m here, and then you end up with an m inverse on the right, on the left-hand side. Yeah, good question. Thanks. Okay. So now, rather than going through the same process that I went through in lecture for the scalar case, I want you guys to go through the same steps, but for the vector case, right? To basically prove the solution involving the matrix exponential that we have here. So we start with this general initial value problem, and then we get to this solution here. And again, like you can probably just pull up the slides, whatever it is, 12 through 16 or something like that, where I did the scalar derivation, and you just go through step by step. But you just have to be really careful and really methodical with the rules for the matrix exponential, with being careful about what's a vector, what's a matrix, what's a scalar, the order in which things are multiplied, and stuff like that. But if you follow the steps and you use the properties of the matrix exponential that I've written down here, you don't need any ones that aren't in the slides. And if you use the product rule, which again, I wrote down a few slides ago, but I've reproduced it here for this kind of weird situation where you have a matrix valued function of time times a vector valued function of time, right? The product rule for that thing has this particular form. So if you use that information and you start with this, you will eventually get to this. And you can probably Google this. I think if you put it into ChatGPT, you'll probably get nonsense, but I'm curious if you get something interesting. Actually, I'm curious as well if Wolfram Alpha or if Mathematica, if it will give you a step-by-step explanation of the proof. So you can use resources like that. You're welcome to do it. I suggest trying it by hand first, and if you get stuck, then going to those fallback kind of resources. But you can talk to each other. You can talk to Priya Darshan. You can come talk to me in office hours. That's all good. There won't be a lot of proofs in this class, but basically there isn't computing for you guys to do in the first couple of lectures because we're just talking about, like, I don't know, theory for solving differential equations. So this time there'll be a little bit of math and then a little bit of computational math and then a proof in this homework. In future homeworks, it'll be like, some math, like formulate some problem in a clean way, and then generally we'll move on to computational stuff, program and a solution and so on. Okay, so just like in the scalar case, we took this general solution that I highlighted here, which this thing is like weird to even think about what it means, right? So we have to be able to compute the matrix exponential to get the thing on the left term here, and then we have this integral in here of a matrix exponential times a vector. So it's like not even clear how you would evaluate this computation. We'll talk a little bit about that. Again, you can use MATLAB basically to simplify that. There are built-in functions that do it for you. But there are some special cases where that formula ends up looking a lot simpler. So if A is invertible, then it turns out we get a cleaner formula for the matrix exponential and the integral that shows up on the right-hand term there. And if B is equal to a constant, we get this. So now this is something that we can evaluate. We can imagine evaluating. So on the left-hand side, we still have the matrix exponential, but again, MATLAB has routines for computing that. So this is basically just a matrix vector multiple. So that's not hard to compute. And then over here, we just have, so again, matrix exponential. This is just a difference in two matrices. That's easy to compute. And over here, we have an A inverse B, is basically solving a system of linear equations. That's usually not done actually by forming A inverse. It's usually done with some more clever numerical method. But anyway, this is all stuff that you can basically compute. Okay, so where does this formula come from? So basically, this is unchanged, and the left-hand side is unchanged. All we did is simplify the integral that showed up in the last term. So let's just talk about basically how that happened. So this is the term, you'll have to believe me, that showed up in the highlighted equation a couple of slides ago. So if A, let's see, what happens here? Oh yeah, B basically is a constant, so it can factor out of the first step. And then to go from this line to this line, we have still the same prefactor multiplying here. We have B on the right-hand side. And so all we've done basically is evaluated this integral from T initial to T of e to the minus tau A d tau. And so this is basically just using the integral formula that I showed you a couple of slides. Let's see. Yeah. So it's using the second one of these, basically. And then the T2, that has value T, and the T1 is T initial. So you basically take this thing and you plug it in here and you get this. Now, we're not integrating e to the TA, we're integrating e to the minus TA, but you can convince yourself that that basically works in the same way that it does in the scalar case. Okay, so that's what happened in that step. Now we just then I simplify this, I guess, a little bit here. So the A inverse B, well, that can come out of these parentheses. Those are unnecessary. And then I distribute the negative sign here. And then you can multiply through by e to the TA. So e to the TA times e to the minus t initial A, by our rules for the matrix exponential, we get that is equal to e to the delta t times A. And then e to the TA times e to the minus TA, that becomes identity. And so those simplify. And that gives us back this form. This is really all that we need to know at this point. So this is a very common formula. Very often A ends up being invertible, and you can just use this thing directly. Now, there are some weird pathological cases you may find, probably not in this class, but maybe in some other future thing that you're doing once you're, I don't know, an engineer or a professor or whatever it is that you want to be. And so I guess because we have like 5 minutes left, I'll just go through this, but just know that this is not something that you really need to know for this class. And there are numerical routines that can do this for you. So again, this is kind of extracurricular. Okay, so this is just the general formula again for the vector linear ODE solution. And in the last slide, we took this integral and we simplified it under the assumption that, that A was invertible. But what do we do with this integral if A is not invertible? So I'll give you the answer first, and then I'll show you where the answer comes from. So the answer basically is to form this new weird matrix A bar, or A big, right? Which has A in the, and this is a block matrix, right? So that's why I talked about block matrices in the early slides. So this is an n by n component up here. This is an n by 1 component right here. So then the number of columns is n plus 1. And then below it, we basically put all zeros. So this is just a row vector of zeros that shows up right here. And that is a 1 by n plus 1 vector. So this whole thing ends up being square and has dimension n plus 1 by n plus 1. Okay, so the way to do it when A is not invertible is to compute this big matrix A bar and then to do the matrix exponential of A bar. And we can always do the matrix exponential. We have stable, fast numerical routines to do that. So we can compute that. And then for weird reasons, it turns out that the integral that we're looking for here, this thing, is just the upper right n plus 1 block of this. So there's like a vector up there, and we just want that, and then that ends up being our integral. So I just think this is really, really cool. Again, not useful. It's just kind of beautiful, I think, the argument for why this works. So I'm just going to run through that in the last 2 minutes, and then you guys can go. So basically, we come up with a dummy variable, y, which is just identically equal to 1. It's just everywhere equal to 1. So the derivative of y, of course, is going to be equal to 0, right? And then we can form a new vector, call it z, which is, so x is an n-dimensional vector and y is a scalar. So this thing, z, has dimension n plus 1. It's a vector, n plus 1. So it's equal to x and then y. And we have a functional expression for x that came from our general solution to the ODE system, right? So x is this matrix exponential thing times x initial plus the integral that we're trying to evaluate times 1, basically. We're just kind of copying and pasting this thing here. And then y, well, it doesn't have any dependence on x initial, so it just has zeros down here. And then it has a 1 here because y is equal to 1. So then we get an initial value problem in z, this new variable. So the initial value of z is just x initial. Oh, this probably should say z of t initial rather than z of 0. But anyway, it's x initial and then 1. That's the initial condition on z. And then we can take the derivative of z. Well, that's just equal to x dot and y dot is 0. So we get all zeros down here. And then x dot is just equal to ax plus b. And y is equal to 1. So when we take b times y, that's just equal to b. So this thing is consistent. It just has the x ODE up here in the first row, and it has basically dy dt equals 0 in the bottom row. And then this thing, the coefficient matrix that multiplies xy, that is the thing that we called A bar in the previous slide. Okay, so now this is a linear initial value problem, a vector valued IVP. And so we know that it has a particular solution. And in fact, this thing is unforced. It doesn't have a plus b kind of term here. It just has a matrix times the state vector. And so its solution doesn't have one of those hairy, gnarly integrals in it because the affine, the coefficient term, is equal to 0. And so its solution we can write down, it's quite simple. And it's just e to the t a bar, delta t a bar, times the initial conditions. Okay, so now we have two equations for z. We have z is equal to this matrix times the initial condition vector. And z is also equal to this matrix times the initial condition vector. And so it follows that this matrix here e to the delta t a bar must be equal to this big matrix here. And this thing, this top right block of the matrix is the thing that we were looking for originally. So it follows that basically this thing is equal to that. And then we can compute this. Again, we can always compute the matrix exponential pretty stably and pretty quickly. So you compute it, you throw away all this stuff, the top left and the bottom right, and you're just left with the upper right portion. Yes?
Didn't you say you wanted the upper right n by 1 portion, or wouldn't that just be upper right? Oh, wait, sorry. I thought you said n plus 1 by 1.
Yeah, no, good. So right, the dimensions of this thing would be n by 1. Yeah, and this is a scalar 1 down here. Yeah, exactly. Anyway, so I think if you look under the hood, basically MATLAB has functions that do this stuff for you. I think if you look under the hood of what the matrix exponential function in MATLAB does, in the case where a is singular, I think it ends up basically doing this under the hood. Okay, so I mentioned 2 homework problems today. One is kind of quick, one is more involved. One is just crunching numbers and parsing equations. The other one is a proof. I hope neither of them are particularly difficult. I haven't decided on the due date yet, but it probably won't be until at least next Thursday or around midnight. I think, is that right, PD? We talked about basically midnight Thursday or just before midnight on Thursday deadline. Okay, so for this one, if we want you guys to turn those in on next week, Thursday, how I would do this is either I would write it up in LaTeX. First you do a pencil and paper solution, you get it wrong 12 times, and then you eventually get it right. And then you take your clean solution and you just type it up in LaTeX, and it should only be like 10 lines for both problems. Or do the same thing, pencil and paper, whatever, until you get a good clean solution, and then write it up, on a tablet, or write it up cleanly on paper and take a picture of it, and then upload either the PDF from your tablet or else the photo of your paperwork. Upload that to Gradescope, or the PDF that comes from LaTeX. Yes.
Are you going to upload like a homework problem statement, or should we just load it?
No, I'll upload a problem statement that has the due date and stuff like that on it. Yeah, it might have a couple more hints than I mentioned here too. But good questions, thank you. Okay, so who feels like totally nauseous from all the math today? 2 or 3 people. Who's feeling perfectly fine? It's all trivial, all easy. Okay. Everyone else is somewhere in between, I guess. All right. So thanks all, and I will see you on Tuesday.